The science of storing and creating solar and wind energy has been around for a few decades, and with each new discovery in these areas, scientists create additional prototypes and seek to develop better ways to generate electricity. However, scientists are still faced with a problem as they work to enhance the cleanest and cheapest methods of generating electricity. This energy can still not be stored. For this type of renewable energy to make a substantial impact, it must be saved so that it may be accessible at any time from any location. Some MIT researchers may develop a revolutionary solar cell that can solve this problem, and guess what? It does not run on sunshine. This groundbreaking solar cell is a new method of generating electricity from any heat source, and it is more than simply a cell that creates electricity. It can also store energy and convert it back to electricity when needed. What exactly is this game-changing technology? How does it function, and how effective is it in storing energy for later use? We have different ways of generating energy from several heat sources such as nuclear energy, natural gas, concentrated solar energy, and coal. The machinery used to generate power from these sources can be challenging to maintain, but the difficulty in operating this machinery is not just the main issue. These energy sources have been the leading electricity supplier worldwide, as 90% of the world's electricity comes from these sources. For technologists to keep extracting energy from these sources, steam turbines are being used. But here is the bitter truth. The steam turbine method has not been operationally effective for several reasons. On average, the steam turbine operates at 35 efficiencies, while the highest efficiency is recorded on a turbine's operation. This decline is due to the massive heat conditions in which the turbines work. The turbines can only run at temperatures of 1,500 degrees, and anything over that causes the mechanism to fail, wasting massive amounts of heat energy. This cause prompted many researchers to keep looking, hoping to find a solution to energy-saving problem of heat engines that can work successfully in extremely high temperatures without difficulty. This is where thermo-photo-volatics come in. Thermo-photo-volatics, also known as TPVs, are like traditional solar cells. They are solar-driven heat engines that harness electrical power from thermal radiation. This discovery was made by MIT researchers led by Asigun Henry, an associate professor of mechanical engineering, in collaboration with the National Renewable Energy Lab. The TPV's principal purpose is to absorb and transform the solar radiation spectrum into a narrow-band thermal emission spectrum that corresponds to the spectral response of a photovoltaic cell. They're regarded as renowned and influential as they have no moving parts and high power capacity compared to steam turbines. They give room to store solar energy with usable alternative fuels that can generate power continuously and make them dispatchable. The primary goal of the solar TPVs is to reduce heat loss from the hot absorber while also making the emitter work efficiently at higher temperatures so that the photons discharged have enough energy. When we look at it on the bright side, we should categorize them as two breakthroughs, not one. The first breakthrough is a comprehensive method of preserving renewable energy. This process begins by channeling a lot of wind into a semiconducting material. A perfect example is a tin. The tin is heated to a very high temperature, above 2000 degrees. This extremely high temperature causes the tin to melt, which is then pumped into a closed-loop system of carbon composite pipes, which leads into an insulated and sealed building filled with massive blocks of graphite. The room where this process occurs is filled with argon gas, which serves to maintain the environment chemically inert by preventing the tin and carbide from oxidizing once the heat is pushed into the graphite. It can remain there for an extended period of time. Because of its layers of free electrons and carbon atoms, graphite is an excellent conductor of heat in this process. Professor Henry also commented on the graphite, saying that the rate at which heat escapes from the block equals its surface area. At the same time, the amount of energy that can be stored is related to its mass. The smaller the object, the larger the surface area is a volume function. This is also why a cup of tea, for example, cools down faster than the Atlantic Ocean. Simply put, for larger objects with a smaller surface area to volume ratio, the graphite block size is said to have covered an area about half the size of an American football field. Cooling the graphite blocks alone would take months, making it suitable for storing thermal energy. The second breakthrough is where thermo-photo-voltaic cells come in. The TPV cells are used to produce electricity. The production of electricity by TPV is done through the following steps. At any point when the grid needs power, the graphite transfers heat from its blocks into a second building containing a line of large, hollow, rectangular carbon-based chambers lined with tungsten foil. Tungsten foil is used in this process because tungsten diffuses protons across a broad spectrum, from high ultraviolet energy to far infrared low points, releasing enough light so the TPV cells can take it all in and transform it into electricity. When the heat is transferred successfully, the tungsten foil glows in full white heat, glowing like the string in an incandescent light bulb. These TPV cells are placed in a chamber known as the power block. Based on the electricity required by the grid, the cells can be raised and lowered simultaneously in the power block. As a result, increasing or reducing light exposure from the hot and burning tungsten foil will increase or reduce light exposure. Although TPV cells are similar to ordinary solar cells seen on our roofs, there are important distinctions such as the substance used to make them. Traditional solar cells are made from silicon. They are turned to have a specific band gap that regulates the wavelength of light that comes into contact with it, causing its electrons to shift from their space into the electrical circuit. Every photovoltaic cell, TPV included, is programmed to absorb photons at a close range, which means that light with higher and lower frequencies is always wasted. Instead of silicon, the MIT team used gallium arsenide, a material that the National Aeronautics and Space Administration uses in conjunction with solar panels in space. Due to its higher absorption coefficient, gallium arsenide can absorb more energy from solar radiation. Simply put, this material can extract energy from the light emitted by the glowing tungsten foil instead of the sun. There are also unique peculiarities about TPV cells compared to traditional solar cells. The conventional solar cells you have at home consist of single junction cells, meaning they have two semiconductors for the p-n junction. Single junction cells are also known to have issues associated with lower efficiency, also known as the Shockley-Kaiser limit. The total efficiency of solar cells is based on the principle of detail balance. The maximum efficiency for a single junction cell is 33.7%, but this is not the case for TPV cells. The TPV cells use several gap junctions to avoid lower efficiency. Henry's team ensured that it was at its best. The team put down more than a dozen layers of several semiconductors to enable them to create two separate cells, arranged on top of each other. Each layer is wired to have a reasonably different band gap. The gap is used to extract an extensive range of a light spectrum. These cells handle this heat as they are built on four sides of a heat sink, a block of metal containing water channels. The water takes heat from the cells as it flows through. The key of the stage is that it travels swiftly enough to keep the liquid from becoming vapor. Even this light was escaping from this technology, but Henry and his colleagues were not going to let it. To collect the escaping lights, they use a reflecting mirror, which caused the lights to bounce back to the tungsten foil before running its core again. This procedure is excellent because it controls light waste while also increasing voltage when the light is transmitted back into the tungsten foil. As a result of this technique, Henry and his team were able to achieve 98 reflectivity. This accomplishment added an extra 10 to total efficiency. When we talk about efficiency, the TPV cell's overall efficiency is proudly well over 50%. If the cells can get to that 50% efficiency mark, a 1 square meter cell could generate around 100 kilowatts. So an arrangement of 30 by 30 modules of about 900 square feet would have an overall capacity of close to 100 megawatts. Also, the graphite blocks can hold enough heat for the cells to keep generating power for close to 10 hours. To put it into perspective, 100 megawatts per hour would be enough to power hundreds of homes for 10 hours. And unlike steam turbines, which can have complex moving parts, TPV cells can deliver energy as needed, just like the traditional solar cells we have in our homes, making them more suitable for grid-scale applications. To enhance efficiency and capture wasted heat radiated by these industries, TPV cells will soon be present and functioning in power plants and smelters. That is our video for today. We hope you like it. So what do you think of these new discoveries? Do you think we'll be able to use it in the future? Share all of your thoughts with us in the comments section below. Well, that's all for now. This is Big Tech Media. See you again tomorrow. Keep in mind to like, share, and subscribe.